Okay. So, hello everyone. Welcome to this edition of ICTS String Seminar. So today we have the pleasure to have Pavel Putrov from ICTP Trieste, and he's going to talk us about holomorphic anomaly in Vafa-Witten theory. So over to you, Pavel.
Thank you for introduction, and thank you for inviting me to give a talk. So in a sense, my talk will be a continuation of Atish's talk last week, but in principle, it can be followed independently. So the talk is based on a joint paper with Atish Dabholkar and Witten, and so let me start by summarizing kind of the goal of our work. So the goal can be formulated as follows. So we want to calculate the following quantity. The derivative of z with respect to tau bar, where z here is a partition function of SU2, what is called Vafa-Witten. Explain in more detail what it is later. Theory on CP2. But very briefly, this Vafa-Witten theory is a twisted version of SU2 maximally supersymmetric four-dimensional Yang-Mills theory. And tau here, as usual, denotes complexified coupling constant in the four-dimensional gauge theory. Namely, tau is 4 pi I divided by g square plus theta angle divided by 2 pi. Okay. And by calculation here, I mean the following. So actually there are two. We want to consider two ways to calculate this. So first is the most direct, calculate from the path integral of the four-dimensional theory on CP2. And the second way is to calculate it from the path integral effective two-dimensional theory on two torus, which is obtained, this two-dimensional theory is obtained by compactifying six-dimensional type A1 2,0 theory. So we know that we know so the second way is related to the first by kind of reverse, because we know that if we can obtain four-dimensional maximal supersymmetric Yang-Mills theory by compactifying 6D theory with 2,0 supersymmetry on a torus. But we can reverse the order compactification, compactify the 6D theory on CP2, and then calculate the partition function of the resulting two-dimensional theory on the torus. But today, because there's a limited time, I will the first method, the most direct one. But in a sense, actually, the second method is a bit easier, because it's easier to study the path integral of two-dimensional theory than the path integral of four-dimensional. But it's easier, but it's also a bit less direct. But in many cases, in many ways, these computations they go in parallel. And also, let me mention that there, so this calculation has the following generalizations, which we also consider in our paper, but for kind of for the clarity of presentation, I just focus on the on this simplest example. But the generalizations are that instead of CP2, we can consider Kaehler with B1 equals 0, first Betti number, and B2 plus equals 1. So CP2 is in a sense the simplest example of such a manifold. And we also can consider from SU2 gauge group to SUN gauge group. So let me start by giving a very brief introduction to Vafa-Witten theory. So as already mentioned, so one should start with four-dimensional n equals 4 super-Yang-Mills theory. So this theory is completely specified by a choice of gauge symmetry, which is denoted by G. So gauge group is denoted by G. So, and later we assume that this is just SU2. But some statements may be easily made first for the general G. And so this this theory has the following global symmetry. Spin 4, which is just a spin lift of SO4 rotations in 4 dimensions, times spin 6 arc symmetry, or equivalently SU4 arc symmetry group. So this is the symmetry which in particular rotates. So the theory has 16 supercharges, and this in 6 symmetry rotates the supercharges. So spin 4 can be decomposed into 2 factors, as usual, SU2 left and SU2 right. And here in spin 6R, one can take one can consider spin 3 subgroup. So this is just, so if you understand spin 6 as the rotations of 6 directions, subgroup is just a rotation of only 3 out of the 6 directions. But of course, spin 3 group is isomorphic to SU2 group. And then, so the Vafa-Witten topological twist procedure can be very briefly summarized as follows. So one can, in one sentence, one can say that what we want to do is identify this SU2R subgroup of R symmetry with SU2 left subgroup of the group of local rotations in 4 dimensions. But let me a little bit elaborate on this. So what this actually means in practice? In practice, this means that on a curved, when you consider theory on a curved space-time, suppose this is the manifold M4. When we put the theory on a curved manifold, we want to background SU2R connection. So the connection for this SU2 subgroup of the global symmetry equal to SU2 left part And so what is good about this twisting procedure is in particular, so this background preserves two 16 supercharges on a general four manifold. And moreover, it actually preserves 4 on a color if M4 is equipped with Kaehler metric. So this twisted series has the following field content. The field content of the so of course, first, of course, it still has as an twisted series, it still has a G gauge field. Which is a connection one form valued in the Lie algebra of G. And then there will be the following bosonic field. So it will be a self-dual two-form field and 3 scalars. And they all transform in a representation of my gauge group. So these fields, they originate from 6 scalars, 6 adjoint scalars in the twisted series. So we know that the n equals 4 supernomials has 6 scalars in adjoint representation, but after twisting, 3 of them effectively became, because of this background, 3 of them effectively became self-dual to form, which has a 3 independent component. And there will be this following Grassmann valued fields. There will be Grassmann valued 2 scalars, 2 one forms, and 2 self-dual 2 forms. Also, everything is an adjoint. And this is obtained by starting from the fermions in untwisted series and twisting them. And so moreover, we actually, for the purpose of our calculation, what we want symmetry of shell, because we want to know how the supersymmetry acts on the space where we do the integration in the path integral. So we want a realization of supersymmetry of shell, and in principle, there is no known off-shell realization of all 16 supercharges. But if one considers just this 2 or 4 supercharges unbroken, remain unbroken after the twisting, for this supercharges, it is possible to find off-shell formulation. And as usual, for off-shell formulation, one needs to introduce some auxiliary fields. And one needs the following auxiliary fields. There will be auxiliarily 1 form field and an auxiliary self-dual 2 form. Again, in adjoint. so far? Okay. So then the partition function of the series has the following expected properties. Property, well, it may look a bit strange, but let me write it. So the property is that function is actually non-zero, generically non-zero. This is actually non-trivial because in many cases, after one twists the theory and considers the partition function, in many cases actually zero because of the Gauss number anomaly. But in this case, the Gauss number anomaly is zero, and the partition function itself is non-zero, so it's non-trivial quantity itself. So one doesn't need to do any insertions, for example, as in Vafa-Witten theory, for example, which obtained by twisting n equals 2 superior theory to get something non-trivial. So just the partition function itself is a non-trivial quantity to consider. Second expected property is that, well, we believe in the S duality of n equals 4 sub-n mills. So this means if one considers the partition function for some gauge group G and this coupling -1 over tau instead of tau, this should be equal to a partition function of the gauge theory with Lagrange dual to G, which I denote by G hat, with coupling constant tau. So G hat is Lagrange dual. So in particular, if G is SU2, G hat is SO3. The third property which we expect, but this is a kind of naive expectation, is that the partition function is holomorphic in tau. And so this naiveness actually can fail, and we exactly will consider the example when it fails, and we'll calculate what is actually equal to this. And so what is the naive explanation for this? So naive explanation is so it's possible to show that the action of this four-dimensional theory can be brought to this form: tau times integral where f is the gauge field strength or trace, and plus a q as some supercharge of something. And from this, it follows that if I take one derivative of s respect to tau bar, this will be a q of something. And then if one calculates the derivative of with respect to tau bar, so this is given by some sort of path integral with respect to phi. So by phi here, I denote the collection of all fields. E of minus s, and then the derivative means that I will have in the integral, I will also have derivative of s respect to tau bar, but this is q of something, and so q here is a supercharge, which is any symmetry this can be understood as a derivation in the space of fields. One can integrate by parts, and if there is no contribution kind of from infinity of your space of all fields, then this should be zero if no contribution from infinity.
Hello.
Fail and yes.
Sorry. So just to go back to one point before, I was just thinking. So you're assuming that here your G is simply laced, or is that maybe you had said already and I missed.
You mean in this point 2?
Yeah, in point 2. Or else the tau will have some factor, right? 1 by tau, if I'm not mistaken.
Yes, I assume that, yes. G is of AD type, thanks, yeah.
Okay. And all the things that you'll be talking about for the rest of your talk so that assumption will still hold. Is that?
Yeah, I will just assume SU2 and SO3.
Okay.
Essentially, yes. Or, well, I mean, more generally, but we also consider more generally in the paper, we also consider SUM, which is also.
Okay, thank you.
SUM and the dual will be SP at PSU. And also, I mean, to be precise, actually in front, yeah, I'm also suppressing is kind of a simple phase factor. There is could be a phase factor which is related to kind of 't anomalies. So. And the so another expected property also kind of naively is that if I take this derivative with respect to, well, let me write it GM4, which is a metric, this is a metric on M4, this is also naively 0. And the argument essentially is the same as in the previous case, because once we represent in this way, so this part is not only just holomorphic in tau, this is only a topological term, right? It doesn't depend on it. By the same argument, one can argue if there is no contribution from infinity, then this is also 0, and this is the in a good situation when there is no contributions from infinity. And moreover, so moreover, in a particular cases, one can give a kind of a more explicit interpretation of this topological environment. So under certain assumptions, those additional assumptions, well, in particular, well, I'm not going to give you most general. This is what is so-called vanishing, like satisfaction of vanishing theorem. And it can be, for example, shown, this is the case when M4 is Kaehler, and as the first Chang class is positive. And so under these assumptions, this one can show that this path integral, again, assuming that there are also no contributions from infinity, this path integral localizes on the moduli space of instantons, and the partition function can be written the following way. So it's the following generating function with generating parameter q, and the coefficients being the earlier characters of moduli spaces of n g instantons. So this is the Euler number. And so in particular, in this case, when this is satisfied, this moduli space is actually smooth manifold, and one can define Euler characteristic in the usual sense. And Q here is, as usual, is related to tau by as e to the 2 pi I times tau. Well, let me just briefly mention that more generally, these kind of vanishing theorems are not for this unity function of so-called what is called Vafa-Witten invariance. And so if you're interested in kind of mass side of the story, so this was only relatively recently were mathematically defined, for example, in the paper by Tanaka and Thomas. Mass. But I mean, let us assume that. So let me kind of, so see what happens if you can just instead of defining kind of physically this z by the path integral, we naively just define this z by this formula, and let's try to calculate this. So, and then try to calculate this for the case of CP2. In particular, for CP2, this is actually condition satisfied. And see what happens.
So how do we know that n is non-negative, or we are not assuming that? This q to the n, this n is non-negative, or it can be negative integers as well?
Well, it's well, what is important here is it's bounded from below. And it's a true, well, it's a, you cannot have instant on, well, yeah, if you consider the solutions of the self-dual equations, your n will be bounded from below.
Okay, thank you.
And so, okay, what happens if we do this? If you are just applying naively this formula for CP2, yeah. So okay, and here is just this. And if f is self-dual, then it's okay. So so for CP2, if I use these formulas. Well, this was a calculation of this moduli space of instantons were calculated in papers by Klechko in the beginning of 90s. And so it can be written as follows. So for SU2 and for SO3, there's F0 of tau here. Where F V with index V, so V is 0, 1 of tau is the following function. So I think this is something which has appeared already. You probably have seen this in the Atish talk. And so where H here are what is called Hurwitz class numbers. Precise definition is not really important for us of these numbers, but I mean there are some known numbers, And so what happens if we try to using this naive form to see if this property about S duality is satisfied? So I want to check if this naive function with coupling -1 over tau, is it equal to SO3 naive partition function? And it turns out it's not the case. And this was kind of originally puzzle. This was a puzzle appeared in the original paper by Vafa-Witten. And but what one can say is almost true. So what does this mean? Almost is that this Fe of tau is a vector valued mock modular form. It has a non-holomorphic completion, meaning that we can replace this Fv of tau with Fe of tau plus some addition, which depends, which is an analytic function of both tau and tau bar. It satisfies the properties that, in particular, if it goes to 0 if I take tau bar to infinity. And so these additions, GV, they have an explicit expression for the derivative, a simple expression for the derivatives with respect to tau bar. It's 3 imaginary part of tau to the 3/2, 16 pi I times eta function tau. Sum n q bar n plus v divided by 2 squared. So essentially, this is so in this part, so this is essentially, this is not will be so important for us, but in this part, I want to refer to Atish's talk, where he explained the basic of this modularity. So in particular, this this thing is roughly can be sort of the shadow of this corresponding modular form. And so assuming, so one can assume that this is so we know that the kind of the so this homomorphicity property is kind of is indeed we see, so it's a bit naive, so it can fail if there is a contribution from the boundary. But the property that it's a modular is more fundamental, because we still expect that the partition function to be modular in S duality of the four-dimensional n equals 4 superangles. So it's natural to assume that this completion, which makes it non-holomorphic but modular, is what gives the full physical partition function. Since we know the derivatives of, if you assume this, and we already know what is the derivatives of this GVs here, the additions, then this means that this gives us a prediction for what should be the derivatives of the, in particular, SU2 partition function with respect to tau bar. It gives us a prediction. But what we want to do, we want to derive, so this is kind of part of the motivation. We want to derive this right-hand side of this anti-holomorphic derivative more directly. So we want to derive. So this was this point. So this was a review of kind of known facts, and now I want to start explaining briefly the derivation. But are there any questions at this point?
Hello. So Pavel, there's also one another thing that we would expect, right? Which is tau goes to tau plus 1 to get the full SL2Z.
Yes.
So that is already true for both FV and GV. Is that?
Yeah, because these things are just determined by, well, they're just determined by kind of overall shift of the power of Q. So they just transform some sort of, respect to T transformation, they just transform as some sort of FV to some sort of, well, let me write in this.
Yeah.
Kind of,
so yeah, so FP
by some sort of matrix 1 and some sort of e to the pi I divided by 2 or something.
Okay.
So it's already
what about the G? What about the G? When you complete it, does something happen to this tau goes to tau plus 1 when you add the GV, the non-holomorphic?
Well, the completion will transform under the same, I believe, under the same matrix.
Okay. Okay. So the tau goes tau plus 1 just holds all the time, and it's only the tau goes to minus 1 by tau, which is somewhat subtle. Did I understand that correctly?
Well, at least in this case, yeah.
Yeah. Okay. Yeah. In this partition function,
yeah.
the Vafa.
Yeah, I'm not super light in general, but I think yeah, it's more. Yeah, at least in this case, the modeling problem is S. But I mean, but of course, we have to keep in account this is not a modular form. It's not invariant, it still forms under, because it's a vector. It's a vector valued model. It transforms with some sort of matrices under T.
Right.
Some phases.
Okay. Okay. Thanks.
Okay, so so we want to derive this the anti-holomorphic derivative directly. Okay, so as yeah, as already briefly have, so this can be explicitly written down as the following integral over the space of all fields on CP2. And so I can imagine, so as usual, one can imagine kind of that this is treated roughly as it would be a finite dimensional integral. In particular, one can introduce some particular coordinates, let's say phi I. And so, for example, one can think about them as some sort of harmonics on CP2 of our fields if we do a harmonic analysis. And okay, so we have the following explicit expression where lambda, yeah, I mean lambda is determined by again, lambda can be explicitly found by using this relation. So it's just lambda can be found on a classical level, and again, Q as it's some operator, some linear operator which acts on your field, so it can be realized in this space. It realized as a certain derivation of some general form like this, and so essentially alpha I determines the result of Q on the phi I, and then by using a Stokes theorem, we can reduce this integral to the integral over the boundary at infinity of the space of fields. And so there will be the integral will be weighted with this well, scalar product of alpha and n, where n is a normal vector to the boundary, and then there will be e to the minus s times l. So you can understand this either as integration by parts or as using Stokes theorem. So by boundary at infinity, I mean that well, your space of fields is infinite dimensional, but one can introduce some sort of cutoff near infinity, so make it make it a compact space, but with a boundary. And but later we want to consider the limit when this cutoff goes to infinity. And so in principle, it's well, this looks a bit too complicated. There are some infinite dimensional spaces, and so it's not clear how to kind of deal with this type of. We still have infinite dimensional integrals, although we reduce it to a boundary. But one can notice one can simplify things by making the following observation: so the non-zero contributions can only appear from the directions where, so we go the direction, I mean direction where we go to infinity in the field space, only direction where only a bosonic zero modes go to infinity. So this, why? Because if you take if you go in some direction where non-zero mode goes to infinity, then it will be suppressed because e to the minus s will go to 0 if we take a non-zero mode to infinity. If a non-zero mode. And moreover, we also don't really care about the kind of boundary in the space of fermionic modes, 0 on the 0. This is because just by definition of the Grassmann integral, this type of expression is just identically 0 by definition for Grassmann, for any Grassmann coordinate. So one can visualize this kind of situation as follows. So we have so one can understand the space of all fields as follows. So there will be a certain finite dimensional base, which is a bosonic, where the bosonic zero modes live. And so this is finite dimensional. But then at each point, there will be infinite dimensional fiber where we have all non-zero modes and fermionic, all fermionic modes, and also all auxiliary modes. For auxiliary modes, they don't have the quadratic part in the action has no derivative. So if you take even zero auxiliary field, even zero modes, this action will go to 0. E to the minus action will go to 0. And so this part is infinite dimension. And so the statement is that when we consider boundary, we only interested in the boundary in this boundary of this finite dimensional space. And because in all these directions, if you come in any of these directions, we cannot get a non-zero contribution. So we should stay here to get a non-zero contribution. Okay, and well, this is kind of a rough, brief explanation. Yes.
So just to make sure that I'm following, so by bosonic you mean Grassmann even and Grassmann odd, bosonic fermionic?
Yeah, this is a Grassmann. This is not this is statistic, not representation wise.
Okay, because okay, fine. And can you, so Can you just remind me what were the bosonic dice, class 1 even dice in this theory? Or
sorry, can you say it again?
I was just, so maybe you are going to tell us again, but what are the bosonic zero modes in this theory?
I will do the counting explicitly later, a bit later. I will tell.
Yeah.
Okay. Yeah. So let's see. Okay, but so first, so okay, what happens on CP2? On CP2, so first one can notice that there are no non-trivial flat connections. Because it's simply space. So this means there is no zero modes of gauge fields. So the only zero modes can come from the fields which are originated from the scalars of the untwisted theory. So okay, let me write it here. All bonds originate from scalars. So in the twisted series, the only bosons we had was a gauge field and the scalars. And therefore, so we can first simplify our calculations that we can use the fact that near the boundary in infinity of the space of bosonic zero modes, we can use effective description in terms of the theory on a Coulomb branch. With gauge group spontaneously broken to U1 in S2. So in terms of the theory, we're interested in the region of the space of fields where the scalar fields are large, and then we can effectively integrate out W bosons and all their superpartners because they have they effectively have a non-trivial mass. And we go to effectively reduce this theory to one gauge theory, but there will be some non-trivial effective action. So it wouldn't be just an action of U1 superreals. And this effective action has the following form. First, there will be the free part, which is, well, this can be considered as a derivative expansion of the effective function. So this is a two derivative piece. And there will also be, for us, will be relevant the four derivative piece. So the two derivative piece is just a free U1 n equals 4 Maxwell theory. Known, and then there will be a four derivative piece which well, denoted like this, n equals 4 WZ, and this can be understood as completion of the minotaur. So the minotaur, in a moment. And there will be high derivative contributions, which one can argue they will be suppressed too much at infinity, so they are not going to contribute to this integral over boundary. And so what is this S n equals 4 WZ term? Well, it's not a single term, it's a derivative part of the action. And so it can be written like this. So the coefficient pi over coefficient pi times NW, and NW is just a number of which is just difference between dimension of the original gauge group and the gauge group on the Coulomb branch, just 2. And this will be integral over, so since it's a Wess-Zumino type term, this will be expressed as the integral form over a 5-dimensional space, which has a boundary being our M4, well, in CP2 in our case. And plus dot dot dot, and so this term is explicitly known. So I will write briefly what is this eta 5 here. But what we will have to do, we will need this. We will need to find dot dot dots. This is actually a non-trivial part of the calculation, and so these the relevant terms in this dot dot dot. So the terms which will contribute to this holomorphic, in particular, contribute to this tau bar, to the holomorphic anomaly, can be found using off-shell supersymmetry, which, as I mentioned, one can explicitly write what is the off-shell supersymmetry transformations for these unbroken supercharges. And so the start of this supersymmetrization procedure, at the start we take this term, which was known perhaps, and which was derived in particular by Zeitlin Zarembo in '99, and also considered in the by interligator in 0. And so one way to derive it is just, in particular, to integrate to do the explicit calculation, kind of integrate out W bosons. And okay, so let me quickly write what this term is. Eta 5 was this form eta 5. So so I will write it in untwisted theory. It's easy to write it in untwisted theory, but with general background spin 6 symmetry, and this is enough to rewrite this term in the twisted theory. In particular, if we denote phi I, where I equals 1, 6, this is the scalars of U1 n equals 4 vector multiplet. So it will be, this term is written in terms of the scalars, but let me introduce also the following notations. For phi hat will be a scalar divided by of this dimension 5 vector, and so dimension 6 vector, and I also need to introduce AR. This is the ground spin 6 R background one-form connection. Okay, and we derivative, covariant differentials. This is a differential, usual differential, plus AB are multiplying 5 factors. So again, here AB is there, just go from 1 to 6 indices. Okay, and then this eta 5 is explicitly can be written as follows. AR is a gauge field strength corresponding to AR, background R symmetry. Two is 3. Okay, and so there's explicit expression for this eta 5, and then I can use it to first to translate it into twisted theory, and then use off-shell supersymmetry to find easy terms in this ... here. Okay, and
sorry, I have a quick question.
Yes.
Is there a coupling constant dependence anywhere in all of this? The tau.
No, there is no. Yeah, it's actually no. There's no coupling dependence. So this is a kind of this term here is actually the coefficient here is robust. It's just quantized actually for this to be well defined. One can also argue that this there is no dependence on coupling constant. That well, this yeah. Let me make the following remark that this term has the following meaning. So this term can be used as a term compensating, which compensates the mismatch of SU4 R Tooth anomaly. Why there is a mismatch? Because if one writes degree 6, so for example, for n equals 4 superpolynomials for general group G, degree 6 anomaly polynomial, it will be of the following form: dimension of group G divided by 2 times class of SU4R. And we see if you go from dimension of SU2, which is 3, to dimension of U1, which is 1, there will be a mismatch. Just a vector, itself doesn't do the anomaly matching, and but this term itself will be anomalous. So it's actually will not going to be invariant under SU4 to actually provide a mismatch. But we know since the coefficient here is quantized, the coefficient in the term is also quantized. So roughly the mismatch can be very loosely one can see the mismatch by writing that the d 5 is actually non-zero, but it's C3. This is kind of loosely, a bit loosely written form, but one can make it more precise. Because this form is not closed, it's not closed for general background R symmetry. That's why it's actually it's a normal. It's closed if the background R symmetry is trivial, but for non-trivial background R symmetry, it's not closed.
Thank you.
And okay, let me make another quick remark. So this full four derivative piece, if one restricts it to just n equals 4 vector multiple, let's say psi. So in principle, it's a piece of the action which depends on the n equals 4 vector multiplet. But suppose we just consider decompose the n equals 4 vector into hyper and vector and put all hyperfields to 0. And then it's a term which can be written in the superspace formalism as follows. And this is something we found quite a while ago by Dine and Zyberg. But this the result is not enough to get the terms which actually contribute to holomorphic anomaly, because the terms which contribute to holomorphic anomaly, they actually vanish if one just restricts to a vector to n equals 2 vector multiplet inside n equals 4 vector. So it's not enough to just result. Okay. So how much time do I have left? Am I over time?
Like 5 or 10 minutes.
Okay, thanks. Yeah, I think I'll take 5 minutes. Okay, so so now we are ready to essentially do the calculation, and yeah, I will be very brief, and I will skip all technical details. But the moral is the following: so as contributions, so as usual, one can use the fact that the contributions from non-zero modes in the path integral cancel due to supersymmetry. The integral reduces to a finite dimensional integral over the zero modes. So what are the zero modes on CP2? So okay, so let me quickly come back to this field content which I wrote before. Okay, so there'll be and we do a count zero modes on CP2. It's easy to do. So again, there is no flat connection, so there'll be no zero modes from here, from the gauge field, and there will be so CP2 has one harmonic self-dual to form, so it'll be one zero modes from here, and of course it has can have 3 constants. There will be 3 zero modes, also 3 bosonic zero modes from here, and similarly there will be 2 fermionic zero modes from these 2 scalars. Again, there's no harmonic one forms on CP2. There will be no zero modes here, and there will be again 2 zero modes from self-dual to forms, and auxiliary fields. One form give nothing, and this what auxiliary self-dual to form will give kind of one auxiliary zero. So this is accounting, and so the result is the following. So there are for bosonic zero modes, which it's convenient to combine in kind of 2x2 matrix with indices going 1, 2, and there will be 4 Grassmann zero modes as we counted, which is convenient to do by chi A and chi bar A. Again, A and bar go from 1 and 2. And there will be 1 auxiliary, which will denote by just H. And then, so everything boils down to calculation of the integral over this finite dimensional integral of those guys, U, chi, and H. And inside the integral, we have all the pieces which we had before. We just restrict them to 0. So we restrict the supercharge on 0 modes, this lambda to the 0 modes, and the action restricted to 0 modes. And okay, there will be some overall numerical factor, and there will be the following factor, eta power being power which is L characteristic of CP2. Well, just this is just 3, and so this can be understood as a contribution of a point like. And well, there also will be a sum. So we need to decompose everything into the sum over n. So the sum over n here is just sum. So n here is a flux of my U1 gauge field through CP1 inside. And so the integral decomposes into sum over all flux sectors, and so it just belongs to an integer. Okay, and so everything here is now everything here is explicitly known, and this is a finite dimensional integral. So in particular, the this action restricted to 0 modes will have 2 pieces. So first, the free action restricted to 0 modes. Okay, I used imaginary part of tau. And H. So just to show that everything can be written down explicitly. And there will be this part which comes from this for derivative pairs, which is when restricted to 0 modes, it's of this form. And finally, this lambda restricted to 0 modes. And Q, well, Q restricted on 0 modes becomes just a finite dimensional, the derivation in a finite dimensional space. And so we can use this expression, but and just evaluate finite. And of course, we use the fact that the Q is a derivative here, so we should integrate by parts again and reduce to integrate one less dimension, and this gives us. And this gives us a finally the expression for the Sandy holomorphic derivative. It is in agreement with the prediction from mock modularity. Okay, so that's all I wanted to say. Thank you.
Okay, thank you very much, Pavel, for the nice talk. So maybe we can unmute your microphone and clap. Okay, so this is the time for questions. So if you have any questions, then you can unmute your microphone and please go ahead.
Question?
Yes.
Yeah. So B1 equals to 0 when to the fact that there is no zero mode for the gauge field, and I guess B2 plus 1, B2 plus equals to 1 went into the fact that in the counting of the zero modes, the Kaehler form was the only one. I mean, apart from the 3 scalars. How do you know this is CP2 and not any other manifold with the same?
Well, this expression is specific for, well, those expressions are specific for. It will be yeah. So these expressions they obtained. They're actually specific for CP2. So they obtained because they're from this guy and this eta 5, and explicitly writing it in this CP2 compound.
I see. Okay.
But I mean, one can generalize this to other manifolds, yeah, with B2 plus equals 1, and those if you do. I mean, the simple case, if you consider simple case when if you do, for example, the assumption that the first term class of the tangent bundle is proportional to the Kaehler form, and then essentially everything will be almost the same, as there will be just extra factors here. So instead of yeah, if you do this assumption, then essentially instead of the difference will be 6 instead of well, 3. What is the factor of 3 here? So like 3 is the most non-trivial thing, right? Because I mean 2 and pi they can appear from anywhere. But 3, what does it mean of C1 of CP2 times omega times the class of omega, where omega is the square root is equal to 1. And this in this way you can generalize this. Like if you assume that C1 of M4 is still kind of proportional to class of Kaehler form, then essentially you just get the same thing with this factor. But if you don't assume this there actually be other terms of a bit different terms.
Thank you.
Any other questions?
Yeah, could you please explain the origin of the summation over n in your final formula?
So this is we have to sum over all. When we reduce to gauge theory, for U1 gauge theory, we need we have a different topological sectors which differ by this of the flux. And this n, for example, it appears. I mean, this the action restricted to zero modes will explicitly appear here because. Yeah. Although the gauge field doesn't have any zero modes by itself, but it's still kind of the integral of f is can be over CP1 can be non-trivial constant.
Right. I mean, in the
Sum over all.
In the expression for the partition function that you had, it was sum over instantons, whereas these are completely different sum over n, right? This is
it's a different. Well, for U1 theory, I mean, the instanton number is so instanton number is can be said as n squared. But yeah, so this is a first chunk class, and the instanton number is a second chunk class of SU2. There was SU2. But in principle, yeah, this is different. So.
Thank you.
Hello.
Yeah. Okay.
Yeah. Sorry. So,
Yeah.
so in this, when you calculate the del z by delta bar, so you have this numerical factor, the normalization.
Yes.
Is that easy to compute? What is the easiest way of fixing that factor?
No, we don't actually in 4D calculation we don't fix the factor. We fix, but it can be fixed in this using 2D calculation.
Okay.
In 2D calculation, you have canonical normalization because you can write partition function as a trace. Because there's a you see a circle there, and like which is a time direction. So you can it's easy to fix the normalization by requiring the trace of the Hilbert space. But here, no, we don't actually we don't fix this numerical factor in 4D. Because it's quite subtle because it's can appear like once we go once one goes from a kind of UV to the Coulomb branch description, you can have a kind of local counter terms which are proportional to something like Euler density.
Right.
Contribute to some overall constant in the partition function.
Okay.
I mean, one can track this kind of. I mean, but it's hard to of the path integral. But it's hard to track what is the. There's some overall constant can appear once one go from SU2 gauge description to one.
Okay, and one more question. Maybe it is evident, but I'm just trying to understand. So, did you integrate over the Coulomb branch somehow, or is that?
Yeah, because I mean, since we are on a compact space, we're not. I mean, you have to integrate over the whole branch. But yeah, essentially, this is the integral of a kind of Coulomb branch of this U kind of Coulomb branch parameters.
Right, and the point is that is there any sense to asking like whether this non-holomorphic part, does it come from some infinity in the Coulomb branch? Some yeah.
Yeah.
I'm not
essentially so this U they live in a well they just in this R4 space therefore, and essentially if you truncate this R4 by some sort of sphere, well actually I mean you can argue that the shape of your truncation is actually doesn't matter, so you will end up I mean topologically this is S3 and you think some form, some closed form on this S3 of the boundary. So this is how you. I mean, you use the fact that this is Q is something U of something, and you can reduce the integral to the integral of the boundary of this R4. Again, boundary means there is no really boundary. Boundary kind of at infinity, so you need to truncate the space and then you truncation to infinity, but we still have a non-trivial limit.
Mm-hmm. Okay. And so, how do you think this generalizes to the higher groups? In SUN, you would have more integrals, I suppose. More all the parameters.
For SUN, well, you can do this SUN. One can do this in a recursive way. So for SUN. For SUN, one can consider breaking. Let's see, SUN1 times SUN2 times E1, where N1 plus N2 equals N, And this breaking, you still have, and you treat, again, if you don't do anything with these SU factors, but you treat these U1 factors the same way as we did it for SU2. And once you do this, you get a recursive relation in this sort of. So this is expressed as a, well, you sum of all such types of breaking, and you get a formula of this times, well, whatever, something like simple. I mean, simple means of this type of, like this.
Okay.
And in this way, it's, in this way, this is essentially very similar to the SU2 case, the calculation.
I mean, I just meant to ask, the Coulomb branch in the general SUN has is kind of complicated, right?
Yeah, but we don't do a complete. We don't do it to. We don't here consider complete breaking. So we don't break SUN to U one at once. I don't know. Maybe one can do this, but this would be a bit complicated. So it's easy to break it kind of in steps like this.
Right.
Yeah, if you do breaking at once like this, then you would get a many more dimensional integral.
Yeah, what I was asking was that there are these special points and special loci where, you know, like you have this kind of breakings, and then in general, the generic point in the Coulomb branch, you're broken into U1 to the power n minus 1 in some sense. Or, so whether, you know, like you should get recursively various contributions from various codimension loci. But you're saying that, you know, like that can all be just circumvented by just writing down such a recursion relation and determining things this way. Is that what you're saying?
Because I mean, yeah, I don't know, because one should be like, if one goes to the Coulomb branch, I mean, the full Coulomb branch, one should be careful with, I mean, what's going on along the loci where the group partially get restored. So,
right.
I mean, yeah, I don't know. If one does this carefully, maybe one can do this like directly going here.
But I was wondering whether there's a sense in which it localizes to some loci versus other loci. That is, things like there's no such result. Is that right? I mean,
no, because really it expresses. I mean, this is still kind of not. This is just expresses this SUN with kind of lower rank, but it still doesn't give you. I mean, this is a kind of this calculation doesn't give you what these guys are. So it's not really localization of the full thing. It's just you kind of. It's really kind of it gives you just only recursive kind of expression. I'm not here. I'm not really giving a full, like in this case, I just give an explicit expression for the whole thing. But here, it's kind of, I only use it expressing some other kind of essentially unknown quantities. Well, again, these guys in principle one can try to do localization as Vafa-Witten, but it's a bit different type of localization. It's a localization of not on the boundary localization.
Right. Okay, just one more question, slightly off this thing. So can this be, do you think this holomorphic anomaly, if you may call that, can be computed from holography? Like, can I compute it somehow from the 2B theory and twisting it and so on somehow? Maybe with CP2 boundary or something. Like since I know the n equal to 4 is dual to the type 2B in ADS5 plus S5, there should be some way to twist the both sides.
Right. Yeah.
And compute it on the string theory side, maybe reduce it to some topological string theory calculation or something. Do you know whether that's possible?
No, I think it's an interesting question, but yeah, I don't know. I haven't thought about it.
Okay.
I think there was some works, I don't remember, about some sort of holography, but they twist, they consider some n equals 2 theory. They do some twisting.
Mm-hmm.
And I think there was some sort of statement about holography in that case. But I don't remember if they actually were able to really calculate something. I forgot.
Okay, thanks.
Any more questions? Yeah, it seems that there are no more questions. So thank you very much, Pavel, and thanks everyone for joining. So this is the end for today's talk. So I wish you a very nice time and probably see you in next week. Bye-bye.
Thank you.